Hi everyone. So today we will be talking about the last part of our series puzzle, and that is the power calculations or the wattage calculation for your circuit. So I'm going to go back to the solutions that we've had when we had just one resistor and 6 LEDs. And this is the circuit diagram that we had in that solution. So the first thing I want to do is I want to ask you a question. What does resistor do in a circuit? What is its function? Why do we have it in there? So the reason we have a resistor in our circuit is to slow down the current. But in order to slow down the current, it does not actually need to have any kind of voltage. It can have a very small voltage, or it can have a very large voltage. So all the energy that your resistor uses, it actually doesn't use that energy to slow down the current. So that brings me to the next question. What does the resistor do with all the energy that it gets? And its energy is, of course, the voltage drop that it has. So the LEDs use their voltage drops to light up. But what do resistors do? So resistors convert the energy to heat. This is why we can approximate items like a stove or a heater with a resistor, the way they behave. But in the case of this circuit, the heat is not actually something that we want. It's kind of an unintended consequence of using a resistor. So let's figure out how much energy does this particular resistor in this particular circuit uses up. So what is the voltage of this resistor? What is its voltage drop? In order to find its voltage drop, you need to consider the KVL for one of the loops. Now, here's the deal. All the loops in the circuit are going to be absolutely the same because they all contain the same resistor and one of the exactly identical LEDs. So in this loop that I have just outlined, we have only 3 items. We have voltage of the battery, we have the voltage drop of the resistor, and we have the voltage drop of LED. So when you look at this equation, we have 2 items out of 3. We know that voltage of the battery is 6, and we know that the voltage of the LED is 1.84. So the voltage drop of the resistor is going to be 4.16 volts. So this brings me to the power that this resistor is going to dissipate. This voltage is the amount of energy each charge delivers our resistor, and then that resistor takes it in and turns it into heat. But how many volts the resistor will actually turn into heat depends on how many charges are going to pass through and give the resistor that voltage. And that, of course, is the current. So this is what I'm going to do next. In this type of circuit, right, we were the engineers. We were the ones who designed it. So what if I say that my current, I1, is 10 milliamps? Now, in this particular circuit, all the currents have to be the same, right? So if I1 is 10 milliamps, then I2 is also going to be 10 milliamps, and so on. And we have 6 of them. So I1 equals I2 equals I3 and equals pretty much the rest of them. So the next question is, if these are the currents in the branches, the currents that only go through the LED, how much current will actually pass through the resistor itself? So the current that's going to pass through the resistor is I total. Because in order to get to all of the LEDs, each individual current has to pass through the resistor, and they're all passing through at the same time. So I total is 60 milliamps in this case. So now we can finally find the power dissipation. So power is the rate at which energy is used. So it's literally saying how many joules of energy is this resistor using up in a second. And if you're using your energy a little too fast, your resistor is going to overheat and die. So that is why we're even doing this calculation. So the formula for power is current times voltage. But which current? Well, of course, it's the current that goes through the resistor, and the voltage is the voltage drop of the resistor. Think about it this way. The current is the delivery mechanism. So that each electron in that current delivers exactly 4.16 volts to that resistor. And the more electrons do that, the more power it's going to dissipate. So in this particular case, the power dissipation rate of this resistor is the current, which is 60 milliamps or 0.06 amps, times the voltage drop, 4.16. So why don't you tell me how much that is? So what I got is, when I round it up, I get 0.25, and the units of power are, of course, watts. We did this in the second gradient cycle, so you guys should remember that a little bit. So the power dissipation rate of this resistor is 0.25 watts. So now is the key point, right? Now we have to review and figure out which power rating should our resistor have. So power ratings of the resistors come in fractions. So we can have 1/8 of a watt, we can have 1/2 of a watt, we can have 1/4 of a watt. And if you choose the wrong power rating, your resistor is going to overheat and melt. I have seen projects go up in literal flames, like they actually caught on fire, because people did not check their power rating. So 1/8 of a watt is 0.125. So for example, if you look at this circuit, right, and you look at our power dissipation rate, and it's 0.25 watts. So you can see that in this particular case, you cannot use an 1/8 of a watt resistor, because the max rate that that resistor is rated for is actually half as much as what we actually have. So what about 1/4 watt? Well, this is exactly 0.25. But guys, I caution you not to use the resistors right on the very edge of their rating, okay? So it looks like a perfect match, but it's not, because what it's really doing, it's working right at the boundary of where it's about to start breaking up, okay? So if you're working at its max capacity, you're going to wear it out a lot faster. So in this particular case, I would absolutely go with 1/2 watt resistor, so that there is a lot of give in there and a lot of extra space for our wattage. All right. For my next example, I want to do the next circuit. And in this circuit, we have 2 LEDs in each branch. So we're going to have a different voltage drop for our resistor, and I want to specify my current straight away. I want the current in all of the branches. That means I1 and I2 and I3. I want them all to be 5 milliamps. So the first question I have to ask you is, what is the voltage drop of this resistor? In order to find the voltage drop, you once again need to consider the loop. So in this particular loop, you're going to have a battery, a resistor, and this time you're going to have two LEDs. So once you add up these two, you're going to end up with something like 3.68. And that would mean that the voltage drop of the resistor is going to be 2.32 volts. So we have already determined that our current is going to be 5 milliamps. So now all I need to do is to figure out how much power my resistor is going to use. And this is extremely straightforward. All I have to do is multiply the current that's going to go through my resistor times its voltage drop. Well, I'm going to have three little currents going through this resistor at once. So my I total is going to be 15 milliamps. So what is going to be the power dissipation for this one? What is going to be the power for my resistor? So let's plug in the numbers. I've got 1.84, excuse me, I've got 2.32 times 0.015. So what is that going to be? That is going to be 0.0348 watts. So when we are choosing our value for our resistor power rating for the resistor, in this particular case, 1/8 of a watt will absolutely work because 1/8 is 1.25 watts, and this is way bigger than the wattage we get. So you should be asking yourself a question. Well, these circuits that we just solved, they were extremely familiar, extremely similar, right? And extremely familiar, I hope, right? So how come this resistor dissipates so much less voltage, right? And it uses up so much less power than the other one. How come? Well, if you think about it, what does the power depend on? It depends on the voltage drop, and we have deliberately reduced this voltage drop. That's why we put those LEDs in the same branch in the first place. But we have also reduced the number of currents. So both numbers, the voltage and the current, went down when we minimized the number of branches. So that's something to keep in mind.